Welcome, and thank you everyone for coming to the first CUbit Quantum Seminar of the fall 2022 schedule. It's my pleasure to welcome one of our own local researchers as the CUbit Quantum Seminar speaker. And we have a very vibrant and exciting lineup for speakers this year. I encourage you all to go to the events website of the CUbit page. You can see what we have planned. So Rahul is joining us as a speaker, and it's my pleasure to introduce him. He gained his master's and bachelor's from the University of Cambridge at Trinity College in the UK. And then his PhD work was in MIT in the group of Levitov. He then spent a postdoc in the Princeton Center for Theoretical Science before joining us here at University of Colorado. So we're lucky to have him back because he's officially not working right now. He's on sabbatical and was spent the last couple months at Stanford. So maybe this is a donation of your time. So thank you very much. His research interests, I believe, he'll probably be able to say more about this, started with graphene and interactions in dipolar graphene, or interactions in attractive graphene. And then he's moved on to many-body physics and systems that I think he's going to talk a little bit about today. So the graphene work especially impressed me because I saw that it was the cover of Nature Physics. So there's a very, very nice illustration graphic that was fun to look at. So so thank you very much, and looking forward to hearing all the great work.
Thanks for the invitation. It's nice to be here, close to home, and to have a chance to tell you about line of research that I've been pursuing for several years now, for which the tagline, I guess, is Fracton Dynamics. So just to set the stage, I'm a condensed matter theorist, and the guiding slogan for condensed matter is the idea that more is different. You take many degrees of freedom, allow them to interact, you get qualitatively new sorts of phenomena, emergent phenomena, and you can view condensed matter theory as really the search for new sorts of emergent phenomena. And historically, condensed matter theory, and specifically quantum condensed matter theory, which is the kind that I do, has mostly focused on systems in thermal equilibrium, and in that context, we found such emergent phenomena as superconductors and ferromagnets and so forth. But by now, the possibilities in thermal equilibrium are relatively well understood. And in contrast, non-equilibrium many-body quantum systems are terra incognita, and they can support qualitatively new sorts of phases of quantum matter. For instance, something we pointed out about a decade ago now is that some familiar types of ordering, which are prohibited in thermal equilibrium, can actually arise in the non-equilibrium setting. And I guess the most famous of these new sorts of ordering are the time crystals, but there's many other examples following on from our original work. And I would really say that understanding non-equilibrium many-body physics and the phases of matter that can arise in the non-equilibrium setting is a grand challenge for condensed matter theory in the 21st century. And the way I'll organize this talk is as follows. I'll begin by introducing you to one of the foundational questions and foundational concepts in non-equilibrium many-body quantum mechanics, and those are the notions of quantum thermalization and ergodicity. I'll then provide a quick introduction to fractons, which are a new sort of phase of quantum matter. I will then explain how we may use principles derived from the study of fractons to understand how to robustly break ergodicity. I'll then introduce you to a new subfield, which I call fracton hydrodynamics, before finally concluding. So, start off by discussing many-body quantum dynamics, and I'll start by asking a very basic question, which is, suppose you have a well-isolated quantum system. So this is my model quantum system. It's well isolated from the environment. It has many degrees of freedom. The state is described by some wave function psi. The wave function evolves in time according to the Schrödinger equation of the system, which is written down over here. Does this isolated many-particle quantum system come to thermal equilibrium at long time or not? And if it does go to thermal equilibrium, then how does it do so? And there's a very basic objection that you can raise, which is, look, the process of going to equilibrium is associated with a loss of memory of the initial conditions. Yeah? If I have a coffee cup, I pour cream into it, I wait a while until it's equilibrated, it's gone to some uniform light brown color, and I cannot extract details about the initial condition. Whereas quantum mechanical time evolution is unitary, which means that formally it preserves all information about the initial condition for all times. But this is an objection that has a well-known answer, which is that, well, actually the only measurements that we're able to make are few body measurements, typically on stuff that's local in real space. And so the key question is, can we reconstruct information about the initial condition by making accessible few body measurements or not? If the only way to extract information about the initial condition is to measure global operators, to measure Avogadro's number of degrees of freedom, well, that's really not even in principle possible. Yeah? So the meaningful question is, do accessible local measurements on a many-body isolated quantum system appear to see a system in thermal equilibrium at long times? And this leads us to the notion of quantum thermalization, which is really all about subsystems. So we have a big quantum system, and we divide it into some subregion A on which we are making measurements, and everything else B. And then we ask if measurements made on A appear to see thermal equilibrium or not. So that's a question about the reduced density matrix on A. And really this all comes down to whether B can act as a reservoir for A or not. If A can exchange energy and particles with B, then we're back to the sort of standard setup for quantum statistical mechanics that you learn in the textbooks. You have a system that's coupled to some reservoir, which is now internal to the system itself. And there's strong numerical evidence that many isolated quantum systems can thermalize in this way. And if quantum thermalization occurs, then the usual sort of lore of thermodynamics and statistical physics, which you learn in graduate stat mech, that all applies. Now, I want to introduce you to a concept that's intimately bound up with thermalization, and that's the idea of ergodicity. So now this is going back to Boltzmann and Boltzmann's work in the late 19th century. So if you have a many-body system, it has macrostates and microstates. The macrostates are characterized by the measurable properties of a physical system, like temperature and pressure. The microstates contain detailed information about every particle. And there's enormously many microstates which correspond to a given macrostate. So you could rearrange the air molecules in this room in all sorts of ways while maintaining the temperature and pressure. And there's a foundational idea in statistical physics, which is the idea of ergodicity, which says essentially that the system explores all of the microstates consistent with the conservation laws. So you have a system with a given energy density, let's say, and it'll explore all the microstates at that energy density. And if ergodicity is obeyed, then we can apply standard statistical physics. Whereas if ergodicity is broken, well, now we're into here there be dragons territory. Yeah? So the question is, how can you go about breaking ergodicity? And if you had asked me this question 5 years ago, I would have said that there is essentially two general ways in which you can break ergodicity in a quantum many-body system. The first is integrability. So this is something we've known about for almost 100 years. If you have a many-body quantum system and it has infinitely many conservation laws, then you don't have ergodicity in the usual sense. Yeah? But A, this relies on infinitely many conservation laws, so it's highly fine-tuned. And B, we don't know how robust this is. It could be if you have a thermodynamically large integrable system, you perturb it even a little bit, and the integrability goes away. Ergodicity could be restored. There's a second route to ergodicity breaking, which has received a lot of attention in the past couple of decades, and this goes by the name of many-body localization, not the topic of today's talk. So this is something that happens in quantum systems with strong disorders. So you have strong randomness and inhomogeneity in the system. And this is a phenomenon which is provably robust in a certain sense. It's robust to short-range interactions, but it's only proven to be robust in a very restricted class of settings. So only in one-dimensional spin chains with strictly short-range interactions. Yeah? So a very restricted setting, but in that restricted setting, it's provably robust. And again, it involves infinitely many conservation laws. So in this case, instead of being put in by hand from the beginning, the conservation laws are emergent, but there's still an infinite number of conservation laws. And if you'd asked me 5 years ago, I would have said this is it. This is the only two ways we know of to break ergodicity, and they're both like pretty delicate. But in the past couple of years, we've actually found a new route to ergodicity breaking, which is robust in a sense that I will explain. And moreover, unlike these two routes, it does not rely on having infinitely many conservation laws. In fact, you can get away with just finitely many conservation laws, and by finitely many, 2 is sufficient if you pick the right 2. Yeah. And the key insights for how to do this come from the study of a new area of physics, which goes by the name of fractons. Yeah? So the goal is to find a new way to robustly break ergodicity, and I claim that the insights for how to do this are going to come from the study of fractons. So now let me tell you what fractons are. So fractons are a new sort of phase of quantum matter, which were originally discovered in 3 space dimensions, although now we know how to get much of the signature physics in lower dimensions as well. And their defining characteristic is that the elementary excitations exhibit fractionalized mobility. So you have excitations which are immobile in isolation, but collections of excitations, like bound states of different excitations, can move about freely. Yeah? And I'll illustrate how this happens in detail soon. And as I will point out, this hallmark property of fracton phases, it provides a new way to robustly evade equilibration and break ergodicity, and a new route to non-equilibrium phases of matter. And once you, sort of inspired by fractons, once you understand how to do it, you then realize that you can actually get the necessary physics even without any fractons in the picture at all. Yeah? So this is inspiration and scaffolding, but once you've sort of reached the top, you can remove the ladder. Yeah? Okay, so now we come to what is probably like the most technical 2 slides of my talk. Don't be intimidated, we'll get back to sort of simple stuff first, but it's nice to have an explicit constructive example, and that's what I now want to present. Yeah? And what I am now going to present is, believe it or not, the simplest known exactly solvable model of a fracton phase. Yeah? Note the words exactly solvable. This is not really simple, but it has this nice property that it's exactly solvable, so you can make exact statements and nobody can argue with you about it. So this is a model that goes by the name X-cube. It's a model that's defined on the cubic lattice, so 3-dimensional cubic lattice. And on every link of the cubic lattice, you place a single qubit, a single spin-half variable. Yeah? And so you have some wave function of all of these qubits, and the dynamics of this wave function is generated by a Hamiltonian. The Hamiltonian is written in the following schematic form. It has 2 sorts of terms, A's and B's. The A term is the product of Pauli Z operators on the 12 links that frame an elementary cube. And the B terms are the product of Pauli Z operators on the 4 links that come out of a given vertex and sit in a given plane, either xy or xz or yz. Yeah? And the Hamiltonian is the sum of all possible A terms and all possible B terms. And you can readily convince yourself that every term in the Hamiltonian commutes with every other term. So you can label the eigenstates by the eigenvalue under all of these terms, and this is the sense in which the model is exactly solvable. And then you can perturb in various ways and make exact statements about the properties. And now let's just consider that for this Hamiltonian, it is made up of A's and B's. The wave functions are simultaneous eigenstates of every single A and every single B. Each A and each B has the property that it squares to 1. Yeah? So the eigenvalues have to square to 1, which means the eigenvalues are either +1 or -1. And for the ground state, to get the minimum possible energy, you give it eigenvalue +1 under every single one of these terms. Okay. So we start with a system in the ground state. It has eigenvalue +1 under every single A or B operator. Now we consider coming in and acting with a single Pauli Z operator on a single link. Yeah? Now Pauli Z commutes with the B operators because they're made up of Pauli Z's, but it anti-commutes with every A operator that shares this link. Yeah? So after we act with this Pauli Z, these 1, 2, 3, 4 A operators are now excited. They now have eigenvalue -1 instead of +1 on these 4 cubes. Now we come in and act with another Pauli Z. Yeah? Now we've anti-commuted once with these 2 guys, so these 2 guys are excited. We've anti-commuted once with these two guys, so they're also excited. We've anti-commuted twice with the two in the middle, so those are back to eigenvalue +1. Those are happy again. And we can go ahead and we can act with a whole membrane of Pauli-Z operators. And every cube in the interior has had 4 anti-commutations. -1 to the 4 is +1. Every cube along the edge has had 2 anti-commutations. -1 squared is +1. But on the corners, we've had a single anti-commutation. So on each corner of this membrane, we have a single isolated excited cube, a single cube where the A operator has eigenvalue -1. And now if we try to move these cubes around, you stare at it for a little bit, and you can see that if you act with the Z here, that'll move this cube down over here, but it'll also create 2 more excitations. So there's nothing that you can do which moves a single cube excitation around other than expanding, contracting, or otherwise deforming this entire membrane, but that's a highly non-local operation. And usually, when we're doing many-body quantum mechanics, we're limited to things that are local in real space. So these single isolated cube excitations are immobile under local Hamiltonian dynamics. Okay, so that's essentially the end of my very technical aside. Now I'll go back to stuff that is hopefully easier to follow. So the fact that you have these cube excitations which are immobile under local perturbations, that endows the system with slow dynamics. Every time you try to move one of these cubes, you create additional excitations. If you're at 0 temperature, then that costs energy. There's nowhere to get the energy from. So these individual cube excitations are perfectly immobile. At non-zero energy density, what happens? Well, that's a problem we tackled in this paper here using methods drawn from the study of many-body localization. Shorn of the technical details, I'll just give you the answer. And the answer is the system does, in fact, thermalize. It is ergodic, but just the time scale on which it thermalizes is very long. And as you take temperature to 0, it diverges as exponential n1 over temperature squared. So it's sort of faster than exponential divergence of the equilibration timescale. Well, that's very well. Long timescales are good as some kind of glass, but I promised you ergodicity breaking, and this is still ergodic. So this is not ergodicity breaking. And to understand how to actually get true ergodicity breaking, we need to deform the model a little bit, and to figure out the right way to deform the model, we need a different way of thinking about the problem. And the right way to think about the problem uses another familiar toolkit to physicists, and that's the language of gauge theory. So I should say that this is a way of thinking that was come up with by Michael Pretko, who was a postdoc here a few years ago. So in familiar gauge theories like electromagnetism, which you learn about in freshman physics, I guess, you learn Maxwell's equations. So in Maxwell's equations, there's a Gauss's law constraint, which says essentially that electric field is sourced by charge density. And what's not emphasized, but is true, is that this Gauss law constraint actually encodes a conservation law, and that conservation law is conservation of charge. So if you integrate the charge in a volume, you can use Gauss's law to rewrite this as the volume integral of the divergence of the electric field. And now you can use the divergence theorem from vector calculus to rewrite this as a surface integral of the electric field. And now you can say that, well, if the electric field on the surface of your sample is fixed, then the charge enclosed by that surface must also be fixed. So charge is conserved. Okay, so normal gauge theories are written in terms of ordinary vector gauge fields, like the electric and magnetic fields. But what if we wrote down a gauge theory where the gauge fields were, instead of being vectors, instead they were tensors, like matrices, of higher rank objects? So this is what Michael Pretko first considered. He said, well, let's consider gauge fields that are, let's say, symmetric matrices. So in that case, my electric field is now a 2-index object. It has an I and a j index. And the Gauss's law should look something different. Maybe it'll look like this, just balancing indices, di, dj, eij. And this encodes, in addition to conservation of charge, it encodes additional conservation laws. And in particular, it encodes conservation of the dipole moment of charge. And the easy way to see that is to note that if you take dipole moment is given by the position-weighted integral of charge density. So you use the Gauss law to rewrite it like this. And now you do an integration by parts. And after integration by parts, you end up with a pure divergence. And now you can say, okay, you can use the divergence theorem if the electric field is fixed on the boundary, then not only is the charge enclosed conserved, but the dipole moment enclosed is also conserved. So Michael conjectured that you should think of, so dipole moment being conserved as an interesting consequence. If you have a charge and it's sitting here, that charge cannot move, yeah? Because if the charge moves either left or right, it changes the dipole moment. Whereas if you have a plus charge and a minus charge sitting close together to make a dipole, that dipole can move freely. Yeah? And this is the hallmark fracton property. Individual charges cannot move, composites of charges can. So what Michael conjectured, and you can make this rigorous in various ways, is that you should think of the key sort of properties of fracton phases as arising from conservation laws on multipole moments of charge. Yeah? Okay. So that this was Michael's big idea. And the exactly solvable models, like the X-cube model or the other stabilizer code models, they have conservation laws on multipole moments of charge, but they're discrete conservation laws. They're like Z2 type conservation laws. And the real payoff comes if you move from these discrete Z2 type conservation laws to continuous U1 conservation laws, like you have for electric charge in Maxwell electromagnetism. Yeah? So Z2 conservation means charges are either 0 or 1. Like two charges, you put them on top of each other, that's the same as 0 charge. Like U1 means you have 1 charge plus 1 charge gives you 2 charges. Yeah, they don't. So you need to move from Z2 conservation laws to U1 conservation laws. You want to consider conservation of U1 charge and dipole moment. Now this may seem very formal and very baroque, but as we will shortly see, it actually has multiple natural experimental realizations, the simplest of which is ultra-cold atoms in a tilted potential. Yeah? So I'll come back to that, just hold that in your head. So we want to consider, so what we take away from this detour into fractons is that it is interesting to consider quantum dynamics, which conserves charge and dipole moment. Yeah? And as is common with studies of quantum dynamics or many-body quantum physics, we also want to consider quantum dynamics that is local in real space. Yeah? So everything should be made as simple as possible. So let's consider the simplest model, which abstracts everything, all the other complexities away and just distills down to these basics. We want charge conservation, we want dipole conservation, and we want spatial locality. Yeah? So I'll consider a model of one-dimensional quantum dynamics. So think we have some one-dimensional spin chain or some one-dimensional chain where I have a bunch of qubits on a line. I'm going to generate the dynamics using local gates. Yeah? So you can think of sort of quantum circuit dynamics that builds in spatial locality from the start. And I want the gates to conserve both charge and dipole moment, where the charge could be, let's say, the Z component of these spins, or the Z component of the magnetization of these qubits, and the dipole moment is the position-weighted Z component of spin. And again, we'll have this hallmark property that an individual charge will be immobile, because if you move a charge, it will change the dipole moment. Whereas if you have a plus and minus charge close together, that can move freely. Yeah? And you'll also have the key physics that, this, which you could interpret either as charge moved to the left emits minus plus dipole to the right, or charge moved to the right emits minus plus dipole, emits plus minus dipole to the left. These are dipole conserving processes. So let's write down the simplest possible model which implements charge conservation, dipole conservation, and spatial locality. So the simplest way to do it is to write down a quantum circuit model. Yeah? So we have some wave function on all of these spins, which encodes the state of the system. We act on this wave function with a bunch of gates, which you can think of as little unitary matrices. Those generate the time dynamics. Each of these little unitary matrices is required to conserve charge and dipole moment, but other than that, it's completely random. Yeah? So this is random circuit dynamics. Now, if you're not used to thinking of quantum circuit dynamics, you can think of it as you have unitary time evolution, e to the IHT, and you can trotterize the unitary time evolution matrix, and that also gives you something like that. Yeah? So you can think of this as a trotterization of Hamiltonian time dynamics, constrained to conserve charge and dipole moment. And now you can ask, what should we expect to get? So this is something we looked into in this paper over here. Okay, what should we expect to get? Well, this is minimally structured quantum dynamics. Yeah? We're generating the dynamics with random gates. Yeah? So in fact, if it's random gates, we don't even have energy conservation, because energy conservation is the conserved charge associated to translation invariance and time. If we're choosing these gates at random, then there's not even energy conservation. Yeah, so there's no conservation laws apart from charge and dipole moment. We might expect that for the sort of minimally structured dynamics, we would have ergodicity. What does ergodicity mean? Well, now, of course, the dynamics is going to be restricted to a symmetry sector, so you start the system off with a given charge and dipole moment, and it can only explore microstates with the same charge and dipole moment. But you might think that the long time average would look like some sort of equal, like the system spends equal time in every microstate with that charge and dipole moment. Yeah? And if you look at the charge distribution, in an equal weight superposition of all the microstates with a given charge and dipole moment, then it looks something like this. The charge is uniformly spread over the system. But then you can actually do the dynamics. You started off with the charge on a single site, let's say site number 4. You generate the time dynamics, you see where it goes, and you find that at long times, the charge settles down to something like this. And this plot on the right does not look like the plots on the left. Yeah? If you were exploring all of the microstates with a given charge and dipole moment, then you would end up with the charge uniformly spread over the system. Yeah? Whereas what actually happens looks very different. It looks like the charge stays close to where it started off. So ergodicity is somehow being broken. So this is something we first observed numerically. In fact, for this minimal model that I gave you, it turns out that almost any initial condition has this ergodicity breaking property. If you start to deform the model, you introduce longer range terms, then you can actually get thermalization for typical initial conditions, but there's still a large class of counterexamples. There's this exponentially huge space of initial conditions which does not thermalize and exhibits ergodicity breaking. And note that this cannot be integrability, because there's no fine tuning, there's no infinitely many conservation laws. And it cannot be localization because localization really relies on energy conservation, and I don't have energy conservation here. So the explanation for what's going on came in this paper here, which we wrote about a year later. And I'll give you the argument here. It's a sort of nice pictorial argument. So remember, we're considering quantum dynamics with charge conservation, dipole conservation, and spatial locality. Yeah? So let me consider a state of the following form. So here, plus is the state which has locally maximal positive charge, and minus is the state with locally maximal negative charge. Yeah? So if I was doing Fermi-Hubbard model, then plus is the state where I have a fermion on the site, and minus is the state where the site is empty. If I was doing a spin 1 chain with SZ being my conserved charge, then SZ is plus S is plus, and SZ is minus S is minus. Yeah? So I have my state of maximal positive charge and my state of maximal negative charge. And let me consider a state that looks as follows. Plus, 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 minus, 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 plus, plus, plus. It's a state that alternates between regions of plus charge and regions of minus charge. Yeah? And it's labeled by some pattern of domain walls, which is domain walls are places where the pattern changes from all plus to all minus. Yeah? And now we want to consider the quantum dynamics of this state. So remember, we're going to generate the dynamics with some gate model, some gate model dynamics. And I've set this up so that the domain walls by construction in this state are further apart than the gates I'm using to generate my dynamics. So I come in and I act with my gates, and every gate acts across either 0 or 1 domain walls. It can never act across 2 domain walls because the domain walls are further apart than the biggest gates I have in my system. Yeah? If I was doing Hamiltonian dynamics, what this would mean is that I've picked a state where the domain walls are further apart than the biggest operator in my Hamiltonian. So when I'm acting with the Hamiltonian, my operators only ever act across either 0 or 1 domain walls. Now, if I act across 0 domain walls, I act on a region that's locally extremal charge, so like locally maximum charge, but the gate has to conserve charge, so there's nothing you can do to this, so the gate must act trivially on this region. If I act across 1 domain wall, then I act on a region that's locally extremal dipole. Things I could do consistent with charge conservation would be deleting plus and minus charges in pairs, or swapping them around. But here, every plus charge is to the right minus charge, so that's locally extremal dipole, and any of those things will change the dipole moment. So again, the gate must act trivially across 1 domain wall. So in fact, every gate acts trivially on this state, which means this state is an exact eigenstate of the dynamics. Yeah? Any state which alternates between pluses and minuses with all the domain walls further apart than the biggest gate in the system must be an exact eigenstate of the dynamics. How many states like this are there? Well, it's easy to get a lower bound. Yeah? So if your gate size is m, then you take your system of size L and you carve it up into blocks of size m, and each such block can be either all plus or all minus, and this gives you a number of such states, which is just simple product states, yeah? But they're also exact eigenstates of the dynamics, and there's exponentially many of them in system size. Yeah? So, the number of symmetry sectors is only polynomial in system size. The number of such exact eigenstates is exponential in system size. You started off in one of these eigenstates, you're not going to explore any other microstate whatsoever, right? You've manifestly broken ergodicity. And this dynamics is manifestly robust to any perturbations that respect charge conservation, dipole conservation, and spatial locality. Okay, we can examine the time evolution in more detail. Now, the time evolution in quantum mechanics is always generated by a unitary matrix. The unitary matrix always is block diagonal by symmetry sector, and in ergodic systems, that's it. Yeah? So it's block diagonal by symmetry sector, and within each symmetry sector is just a random matrix theory applies. Here, what happens? Well, what you get is within each symmetry block, you have a further massive block diagonalization of the unitary matrix. So you have all of these 1-by-1 subblocks, which are these exact eigenstates, which don't mix with any other state. And then you have blocks of size 2, size 3, size 10, size 30, size 5 million, blocks with size that diverge in the thermodynamic limit. Yeah? So you have this exponentially broad distribution of subblocks. And then you pick an initial condition, and the initial condition lies in some subblock, and it can only explore other states within the same subblock. It cannot explore any other states in any other subblock, even if they have the same symmetry quantum numbers. Yeah? So that's the sense in which ergodicity is broken. You might wonder if any of what I was talking about is particular to one dimension. It is not. The construction generalizes constructively to higher dimensions. So the simplest thing you could do is you could go to d space dimensions, you conserve the charge, you conserve all d components of dipole moment, you can straight away write down these sort of stripe-like states. These are exact eigenstates. There's exponentially many of them in system size. Turns out you can also allow the domain walls to roughen a little bit, and they remain exact eigenstates. So this gives you a number of exact eigenstates that's exponential in system volume, and the construction generalizes to arbitrary d dimensions. So if you're in d space dimensions, and you have charge conservation and conservation of all d components of the dipole moment, and your dynamics is generated sort of locally, then you have a number of these exact eigenstate initial conditions, which is exponential in system volume. And then you have this whole breakup of Hilbert space where each symmetry sector sort of breaks up into exponentially many subblocks, many of them 1-by-1, 2-by-2, like broad distribution of system sizes, all the way to subblocks with size diverging in the thermodynamic limit. And if you add conservation laws and additional multipole moments of charge, then you get even richer physics. Okay, so now this is all interesting as a point of principle. You can get this robust ergodicity breaking, which just comes from the interplay of two conservation laws and spatial locality. Can any of this show up in experiment? And in fact, yes, it can. So the simplest realization, again, there's more than one possible realization, but the simplest realization is you have ultra-cold atoms in a tilted potential. Yeah? So you have cold atoms in an optical lattice, you have a tilted potential, and the tilted potential couples to the center of mass. So the center of mass is like dipole moment. If the potential tilt is strong, then if the center of mass moves either up or down in the potential gradient, then it changes the energy of the system. Yeah? Because the center of mass is moving either downhill or uphill. But if this is an isolated quantum system, then you can't change the energy. Energy has to be conserved. So it follows from energy conservation that if you have cold atoms in a strongly tilted optical lattice, then you should get effective center of mass conservation, and center of mass conservation is analogous to dipole conservation, and essentially all of the same arguments apply. Yeah? I should say, like strictly speaking, the conservation law is not exact. It's a pre-thermal conservation law, which means that the dipole moment or center of mass is conserved up to timescales that are exponential in the tilt, but exponential in the tilt can very rapidly become longer than experimental timescales. Yeah? And in fact, the signature physics with these exact eigenstates, so the signature physics here is that the quantum dynamics is exquisitely sensitive to initial conditions. You pick an initial condition, which is one of these exact eigenstates, and you have no dynamics at all. You change the initial condition a little bit, so you live in one of these large subsectors, and it appears you have thermalization. And you have this extraordinary sensitivity of like whether you thermalize or not to the initial conditions. And this has actually been observed already, both in Monica Eidelsberger's group in Munich with cold atoms, and in the Hangzhou group with superconducting qubits. And we also proposed a realization with atomic clocks. There's almost certainly other realizations as well. I'm not claiming this is exhaustive, but this is point of principle that there's at least one setting in which you can actually realize this physics in the laboratory, and in fact, it has already been realized. Okay, so what have I told you so far? I've told you that if you consider these exactly solvable models of fractons, then those give you glossy dynamics, but ultimately you do get ergodicity. And if you want to break ergodicity, then you want to promote to U1 conservation laws. And once you do that, you find that you have this robust ergodicity breaking, which relies on only two conservation laws and spatial locality. And it can be rigorously proven. In fact, I gave you a pictorial proof just in this talk. Yeah? And it doesn't require disorder. It's robust to temporal noise. It's a sort of new and extremely robust form of ergodicity breaking. It does require hard constraints and strict locality, although maybe I should also say that in sort of very recent and still unpublished work, I also know how to get rid of this strict locality constraint. And it can be realized in a pre-thermal sense in various experimental platforms. Okay, so far I was sort of talking about these exact eigenstates. So I said that time evolution is generated by a unitary matrix that block diagonalizes into dynamically disconnected sectors. There were all of these small subsectors, which were these exact eigenstates, but there are also large subsectors, yeah? So subsectors with size that diverges in the thermodynamic limit. And if you look at the dynamics within those large subsectors, you find that it's actually thermal, but it's thermal with respect to the subsector. So you have something which looks like the ergodic hypothesis, but you don't explore all of the microstates in the symmetry sector. Instead, you only explore all of the microstates in that subsector. But if the subsector is of size diverging in the thermodynamic limit, then this can still look a lot like thermalization. And now you could ask, what does the approach to equilibrium look like in this setting? So the canonical theory for describing the approach to equilibrium in systems with conservation laws is hydrodynamics. And the standard long-time behavior is diffusion. And what I've written down here is the diffusion equation for some conserved charge density. Yeah? And now if you just look at this diffusion equation and you do dimensional analysis, you see that there's this characteristic relationship between length scales and time scales, where length goes like square root of time. Yeah? So you can replace the derivative, like rho over time is d times rho over r squared, turn that around, and length scale goes like square root of time. This is standard random walk behavior. This is the behavior you get in the diffusion equation. Yeah? Now, in the setting where you have additional conservation laws like conservation of a dipole moment, then you still have hydrodynamics as your theory for the approach to equilibrium times, but it's not standard diffusive hydrodynamics. Instead, you get new hydrodynamic universality classes, and in fact, there's an infinite family of them, all of which exhibit subdiffusion. And this is a phenomenon that we call Fracton Dynamics and was introduced in this paper here. And now I'll give you a sort of quick overview of how Fracton hydrodynamics works. So we're considering systems with conserved charge and dipole moment. Elementary mobile excitations are dipoles. And the force on a dipole vanishes in uniform field. So if you put a uniform field on, there should be no current, yeah? Which means the conductivity should be 0. And if the system is thermal, we should be able to rely on the Einstein relation. And so if the conductivity is 0, then the diffusion constant better also be 0. Yeah? So it can't be diffusion, it has to be slower than diffusion. What should it be? Well, the dipole current is this 2-index object. Yeah? There's dipoles pointing in direction I, which move in direction j. So you might guess that the continuity equation would look something like this with 2 derivatives. And now we need to figure out how Gij relates to charge densities. And Gij is related to charge densities in this way. It depends on two derivatives of the chemical potential. That follows from sort of standard thermodynamic arguments. Put it together, and you get a modified diffusion equation, which involves the square of the Laplacian. Yeah? And more generally, if you say that I conserve charge in also the first n multipole moments of charge, then you get a generalized diffusion equation, which looks like this, which contains n plus 1 powers of the Laplacian. Yeah? So n is 0 is the familiar case where you only have charge conservation. N is 1 is charge and dipole, n is 2 is charge dipole quadrupole, and so on. Yeah? So you have this infinite family of sort of generalized diffusion equations corresponding to multipole conserving dynamics. And now if you do dimensional analysis on this, you see that distance goes like time to the power 1 over 2 to the n plus 1. So for n is 0, this is familiar square root t. For n is 1, this is t to the 1/4. For n is 2, it's t to the 1/6, and so on. Yeah? So you have this infinite family of subdiffusive relaxations, which get slower and slower as you add additional multipole conservation laws. Can you see any of this? Well, again, I'll come back to my favorite example, cold atoms in a tilted potential. So now, previously I was considering a very strong potential tilt. Now you can consider a weak potential tilt, so the center of mass can move a little bit. In fact, Wasim Bakr did this experiment back in 2020 where he saw t to the 1/4 subdiffusion, and you can very nicely reinterpret the Bakr experiment in terms of this sort of fractonic hydrodynamic universality class that we introduced. And note that there's no 12-spin interactions and no microscopic fractons involved in here. Yeah, so this is a new universality class which we discovered, inspired by fractons. But ultimately, it's a universality class that also applies to very familiar settings like cold atoms in a tilted potential. There's other possible realizations like charged two-dimensional fluids in magnetic field and maybe others that we haven't even appreciated yet. Maybe one little aside that I'll mention. So far I've repeatedly said that there's just two conservation laws, charge and dipole. Actually, there's sort of more. So if you have charge and dipole conservation, and you can define these conserved charges where you integrate the charge density against some function f, and f can be any harmonic function. And by harmonic function, I mean that Laplacian of f is 0. Yeah? And at the level of linear hydrodynamics, it turns out that all of these things are conserved. And there's infinitely many harmonic functions, so there's infinitely many such conservation laws. So you may wonder, well, am I back at integrability? And actually, I'm not, because these things are only conserved at the level of linear hydrodynamics. Yeah? So the moment you put in fluctuation corrections to hydrodynamics, you find that in fact, these things are not truly conserved. They do relax, yeah, but they relax through dangerously irrelevant perturbations, which means that the characteristic exponents for the relaxation can be even slower than the sort of subdiffusive power counting would predict. Yeah. So we already came up with these sort of small exponents for the subdiffusive spreading. Actually, it can be even slower than that because of these additional conservation laws, or these additional approximate conservation laws, so not true conservation laws. Okay, so that was a bit of a technical aside. I'll move on. Okay, so I'm approaching the end of my time, but I'll say, okay, so there's all of these new concepts that we introduced. Some of them you can see in experiment. That's great. Is there any other mechanism through which we can test these ideas? In particular, is there a numerical mechanism through which we can test these ideas? And in fact, there is. So there's a new numerical technique that we introduced really to test these ideas, but I think it has sort of broader applicability. And that's the technique that we call automaton circuits. So what is the automaton circuits technique? Well, the basic problem that we're looking to solve is that, look, if you want to see something like hydrodynamics, you need very large system sizes. How do you do numerics for quantum dynamics on large system sizes? So that's the problem that the automaton circuits technique is designed to solve. So what it says is, let's consider a quantum dynamics that maps product states in a certain basis to product states in a certain basis. Yeah. So if you feed it with product states with sort of no entanglement states in a special basis, then it generates no entanglement. So this should remind you a little bit of Clifford dynamics. Yeah? So for the quantum information experts in the audience, Clifford dynamics takes a product of Pauli operators to a product of Pauli operators. This is the state analog. It takes a product state in a special basis, and it maps it to a product state in a special basis. And if your initial condition is a product state in this special basis, then the time evolution is easy because you don't generate any entanglement. However, if your initial condition is anything else, so maybe the special basis is Z, yeah? If your initial condition is an X basis product state, then it generates lots of entanglement. It's extremely complicated dynamics, yeah? And in fact, right. So in fact, if you explore the dynamics and you don't know what the special basis is, then this dynamics looks, it seems indistinguishable from Haar random dynamics. So you look at the growth of Rayleigh entropies, you look at correlation functions, and you can't tell that you've got the special dynamics as opposed to completely random unstructured dynamics. The only way you can tell is if you know what the special basis is. Yeah? But the fact that there is this secret special basis is in fact sufficient to render the dynamics simulable as long as you know what that basis is. And the way that idea proceeds is as follows. So you consider a generic initial condition. So let's say the special basis is Z. You pick an initial condition that's in the X basis. You make lots of entanglement with the dynamics, so it's not brute force simulable. But what you do is you use Monte Carlo techniques. So you take the projection onto 10 randomly chosen Z basis product states. Each of those you can time evolve efficiently because that's the special basis. And then you average. Take the projection onto another 10, time evolve those and average, and just iterate until you get convergence. Yeah? So you can use the fact that there is a special simulable basis plus Monte Carlo ideas to actually efficiently simulate this dynamics. Yeah? Now this won't work for any quantum dynamics. If you want to know the dynamics generated by the Heisenberg model, I mean the Heisenberg model doesn't have the special basis. Yeah? But you can construct quantum dynamics which have the special basis, yeah, and use it to study whatever properties you're interested in. So if you're interested in what does charge and dipole conservation do, then you can cook up a quantum dynamics which conserves charge and dipole moment, and it has a special basis, and impose no other structure. Yeah, you choose things randomly up to those constraints, and then ask what it does, and you can test it numerically in this way. So this gives a kind of computationally efficient method to simulate certain classes of quantum dynamics in large systems, and you can use it to verify the subdiffusive exponents. In fact, we first saw subdiffusion numerically using this technique, and only later came up with our general analytic framework to explain what was going on. Okay, so to summarize the second part of my talk, when these generalized fracton type systems thermalize, the approach to equilibrium is described by hydrodynamics. So approach to equilibrium in systems with conservation laws is always some kind of hydrodynamics, but it's not diffusion. It's sort of hydrodynamics in a non-standard universality class. It's characterized by subdiffusion, so it's relaxation slower than diffusion, and there's this infinite family of subdiffusive universality classes. We introduced a new numerical technique that's capable of exploring this, and in fact, this has already been observed by Wasim Bakr in at least one experiment. And now to summarize my talk as a whole, non-equilibrium many-body systems are terra incognita. We want to find ways to find new physics in the non-equilibrium regime. We want to find ways to evade equilibration. And the previously known ways to evade equilibration, even to infinitely long times, were integrability and localization. And both of those relied on having infinitely many conservation laws in the system, and they were of a somewhat dubious robustness to perturbations. And we discovered a new way to do it that relies on only finitely many conservation laws. In fact, just 2 conservation laws suffices. So I can bring the number of required conservation laws down from infinity to 2. And this was done using sort of physics inspired by the study of fractons. And the resulting physics is completely robust to any perturbations that respect those 2 conservation laws, and also spatial locality. What you get, so fractons are this new class of quantum states of matter that have the property that elementary excitations exhibit restricted mobility. They were first discovered in the context of these exactly solvable stabilizer code models, but by now we know what the key principles are and how to abstract the physics away to simpler settings. The best known exactly solvable models are in fact ergodic. They just have a very long time scale, but you can cook up new kinds of models. So the exactly solvable models have these Z2 type conservation laws, and the real payoff comes when you promote from these Z2 type conservation laws to continuous U1 type conservation laws. And once you go to U1 type conservation laws, you get a whole wealth of new physics. So you get provable ergodicity breaking. Yeah, so you have your unitary time evolution matrix breaks up into these exponentially many subblocks with a broad distribution of sizes. You have these exponential in system volume exactly localized states, which are exact eigenstates of any dynamics which conserves those two conservation laws and has spatial locality. If you pick an initial condition that's in one of those special ones, or it's in a sort of subblock of finite size, then you have no thermalization at all. If you pick an initial condition that's in a subblock of diverging size, then you can get something that looks like thermalization. But the approach to equilibrium is unusual. It's not given by the diffusion equation. Instead, it's given by some generalized subdiffusion equation, and there's an infinite family of subdiffusive universality classes that you can access in this way. We introduced a new numerical tool to explore this physics, which we call automaton Monte Carlo. It's actually quite versatile. You can use it to explore these sorts of quantum dynamics, also various other sorts of structured quantum dynamics. And the key phenomena have been experimentally observed by 3 different groups. With that, I think I will say that, well, there's still new things that we're finding with fractons, and it's still a wide open frontier. And maybe I should thank the various people that were involved. So a lot of people have been involved over the years with sort of this line of research, but I think there's 4 people in particular who sort of deserve special thanks. So this is Abhinav Prem, who was a student here, then went on to a postdoc at Princeton. This is Michael Pretko, who was a postdoc here, then went on to a job at DoD. This is Vedika Khemani from Stanford, and this is Andy Lucas, our colleague over here. And with that, I will conclude and take questions.
So we have some time for some questions. If you could wait for the microphone for the online, so it's right there.
I wondered for the tilted lattice thing.
Yeah.
When we can assume the dipole conservation is the tilt is stronger than the interaction.
Yeah.
Right. Then I wondered. So is it really many-body quantum effect? Like if U equals 0, you can talk about same thing. And
right. Well, if U equals 0, then this is non-interacting one-year Stark, right?
Yeah.
Or if you prefer, it's block oscillations. So the key thing is, and then you have no dynamics whatsoever, right? So there, it's obvious why nothing happens, because you have a single if it hops right or left. That changes the energy, end of story, right? With interactions, you can actually write down non-trivial dynamical terms. So you could have 2 particles and they could do this. That's allowed. Yeah? You can have correlated hopping or n-particle correlated hopping processes. Yeah? And in principle, sort of any number of n-particle correlated hopping processes will emerge. Yeah? So then there's 2 questions you can ask. Are these correlated hopping processes sufficient to give ergodicity, with respect to this charge and dipole symmetry sector? Yeah, which is not a question that you could meaningfully ask if you had single particle problem. And second, if you do thermalize, what's the approach to thermal equilibrium? Again, there will be nothing like subdiffusion for the single particle problem, because there's just no dynamics, right? The single particle problem, the tilt just completely trivializes it. When you have the many body problem, you can have allowed correlated hopping processes, so you can still have non-trivial dynamics, even in the presence of a tilt.
I see. So you, in the finite U, you're gonna see some kind of crossover, right, of from non-ergodicity to ergodicity.
Yeah. Well, okay. Right. Well, that depends on the initial condition you pick, right? And it also
I see.
depends on how strong the tilt is. But no, for instance, like the simplest non-trivial correlated hopping process is you have two particles and they do this or they do that. That conserves charge and dipole moment. Yeah. So let's say you started with some Bose-Hubbard model with a hopping T and a Hubbard interaction U, right? So you'll just single particle hopping T and Hubbard interaction U. So you'll generate this correlated hopping process in perturbation theory. Yeah. So if single particle hopping is T, interaction is U, and the tilt is F, right? Then I think you'll end up with a correlated hopping process which has matrix element T squared U over F squared. Okay. Or scales like that. Yeah. Which means that if you take U to 0, the correlated hopping process is 0.
Oh, I see.
Right?
Okay, yeah, thank you.
Yeah.
Hi. You put a lot of effort on the fact that you have just 2 conservation laws.
Yeah.
Technically, in every Hamiltonian dynamics, I guess you have 2 to the power of n because you have all the projectors on the eigenstates which are conserved.
Right.
Could you say what you exactly mean by 2 conservation laws?
Yeah, okay. I mean, yes. Strictly speaking, if you start defining projectors onto your exact eigenstate as conservation laws, then every Hamiltonian has the 2 to the n, or like as many conservation laws as the size of your Hilbert space. But that's a silly definition of conservation laws, right? Those conservation laws are completely non-local. So that, I'm going to say that doesn't count. I mean, charge and dipole are conservation laws in the familiar everyday sense that you could tell a freshman that like this is a conserved quantity and it would make sense. So they're made up of stuff that's local in space and integrals of local densities.
So it's always local conservation.
Yeah. Spatial locality is
Thanks.
key.
Over there.
So I wonder for the last part, you mentioned the numeric method called automaton circuits. Is it possible to use it to probe momentum conservation, or is it fundamentally impossible because at the end of the day, you only have discrete translational symmetry?
Okay, so the question is it possible to use automaton circuits to probe momentum conservation? So I think the answer is that it is possible, and I think there is some work trying to do this, but it's not so easy for several reasons. So one reason is that these models are naturally formulated on the lattice, right? So you have some lattice of degrees of freedom. And the moment you have a lattice, you don't have true momentum conservation, you only have crystal momentum. Right? So if you want to have true momentum conservation, then you probably want to define momentum instead as some internal variable that goes along for the ride. But now you have some internal variable with an infinite dimensional local Hilbert space, which is maybe hard to put into your numerics. So I don't think it's so easy to build sort of true momentum conservation, not just crystal momentum, into the problem. But I think there are some papers, by people trying to do this. So I don't know if it's hopeless either. But yeah, if you're satisfied with crystal momentum, it's very easy. So you could certainly consider sort of lattice dynamics and just pick things in a translation invariant fashion, and then you'll have conservation of crystal momentum.
So maybe time for one more speaker, and as a former experimental physicist, I
Right.
gotta ask, you said that there's a new brave new world, wide open frontier.
Right.
What sort of systems should people be thinking that the Fracton Dynamics apply to if you're thinking about, does my experiment satisfy these conservation laws?
Oh gosh. Well, I told you the one that I understand well, which is tilted potential. I mean, I think there's some. I think that's probably the one that we understand best. Are there other contexts in which similar physics could arise? I think almost certainly yes. Yeah. So, for instance, charge dipole. I mean, I think what I generally want is the relevant physics to emerge from some simple principles, right? So that it's obvious, whether it's robust to perturbations or what class of perturbations and how you define this class of models. Yeah? So charge dipole, quadrupole, so these multipole models have a nice sort of obvious principle from which it emerges, and there's some number of context that I talked about in which you can actually realize this. But there's other realizations. So with a couple of postdocs over in Gamma Tower right now, we're working on a sort of problem with a generalized Rydberg constraint, which also realizes sort of very similar phenomena. So
I guess keep that in mind when you're working on your experiments.
Right.
Let's thank the speaker one more time.